All right. What are the kind of things that you want to protect? What are the kind of things that you use cryptography for? Well, data at rest, stuff that you want to keep for long term, stuff that can be used for your business. And also, one of the neat things that crypto does when you're storing data is it may help to compress it, and it'll take up less space, perhaps. And data in motion, data being transmitted from place to place. Crypto can reduce the chance that it's going to be intercepted. It can let you know when it has been intercepted, and it can help obscure the information even if it is intercepted. Two kinds of transmission communication encryption. Link encryption and end-to-end encryption. Which one's better? It's ice cream flavors, right? Depends on what you're doing. Link encryption encrypts everything, including the routing information, and has to be decrypted at each node along that transmission pathway. Theoretically, if an attacker could violate a node, they could see all the messages passing through it in plain text as it's being decrypted to check the routing information before it's encrypted again. End-to-end encryption, even the routing information is obscured. Everything but the routing information is obscured. So it's being sent along a pathway with the cargo enciphered, but not the header. What's the threat there? Well, because that's moving in plain text, you know at least that those parties are communicating. That is a piece of useful information in and of itself, even if you don't know the cargo, right? Okay, the exclusive OR operation. Who can explain it?
It replaces plain text with a new set of data. By comparing the plain text to a key string.
Yes, you are correct. You can put it in hardware instead of software because it is so simplistic. Very straightforward operation. You don't want to reveal the key just by knowing the key stream. If you could extrapolate the key from the key stream, you could also figure out how to decrypt all the other messages that are using that same operation or using that same key. You also want a key stream that doesn't allow predictability. Just because you know the first four, you shouldn't be able to guess the fifth one any better than 50%. Why 50%? Why 50-50?
Something like there's only two.
Yeah, okay, all right, yes. Because we're not using letters, we're using binary digits, right? Good. There should be as many of each of the characters as the others. Also, same thing with repetitions. Otherwise, you're getting that clustering again. You're giving some predictability to it. You're showing trends. You want long sequences with no repetition. Why not? Why not?
Repetition's the death of cryptography.
Yes, yeah. And we've seen that in several implementations of good algorithms, actually. That if you have that repetition, it allows the predictability. It also gives the opportunity for the attacker to try to just use mathematics to interpret your ciphertext. And what does this mean? Each key stream bit, depending on all the key bits. What does that mean? That means the operation should be complex enough to use that whole number. The bigger the number, the more complex the operation, the harder the odds it is to crack any part of it. What's the number of probability of, sorry, let me try that again. When we're calculating probability or likelihood of the outcome of a number, I'm not asking that properly. What's the mathematical expression of the probability based on the size of a binary string of the number of possibilities that you can get from that key.
2 to the n.
2 to the nth. If it's n characters long, n binary characters long, it's 2 to the nth, right? Yes, right? Good. That's stream-based. Why would we use any other form of cryptography? Stream-based sounds great. It's the most important.
You need a really, really big key. It has to be the size of the message.
Yeah, yeah. And what is that prohibitive in some way?
Yeah, you kind of have to transfer the key over as well.
Yes, yes. Basically, you would be sending 2 messages. And then you have to encrypt that, which becomes another difficulty as well. So we use block ciphers instead. We carve up messages into chunks. We encrypt those chunks with a key stream and do the chunks in pieces. Mostly we need software to do this instead of hardware, and it takes up a lot of resources. In this example, our message is message, M-E-S-S-A-G-E. We're going to put the key, an initialization vector, and the first 2 letters, that's our chunk, that's our block, into our process, into our operation. It's going to come out as KJ, and then we have this show up as this. Does that make sense?
By the way, there's an IV.
What?
You asked me.
Oh, that's very good. Thank you. Yes. Good point. There's an IV. We can replicate that. We can duplicate that. We can triplicate that. Do continual rounds of this process to make it even more difficult. What we're going to do is at each point, we're going to repeat that process with the same kinds of blocking each time and come out with a new ciphertext. Make sense? Adding layers of complexity. All right. The key length, simply put, it's how long the key is. It should increase the complexity the longer the key is, for the same reasons we were just talking about. Mathematically, the more possibilities of an outcome from the key length, the more complex it is, the harder it is to decrypt without the key. But again, the longer it is, the more processing power it's going to take. And we have to hit that sweet spot, that cost-benefit analysis of how long is it going to take to decrypt this thing. The block size also affects the security. Why? Why does the number of characters that we're taking out of the plaintext matter? Is it more secure if you take less, a block of a smaller size or a block of a larger size? Now, Matt, now I'm going to pick on you.
Usually a block of a larger size.
You want a larger block, yeah. Less repetition, less chance of repetition, gives you more complexity, and it gives you greater opportunity for transposition inside that block as well. Good. And here's where we see padding. It helps us round up to the next block size set. Each of the blocks have to be of consistent length, so padding helps us bring that out too. We can also add complexity with our padding. There are several different modes, and we're going to get into this in a little bit more detail too, but when we're doing our block ciphering, there's different operations that we can use. There's different ways of adding complexity. In electronic codebook method, it's the least complex. Greg, did you?
It's very bad.
It's what?
It's very bad.
It's bad?
Yes.
Why is it bad? Yes, it is. Why is it bad?
Because your blocks go through the same cipher, and there's no chaining at all.
Good. What does that mean?
If you have this similar plain text anywhere in a message, it'll come out to the same ciphertext, and you can analyze that.
Good, good. An attacker can look at these similar kinds of ciphertext coming out in different areas of the message, and then all they have to do is some mathematical analysis based on the likelihood of those characters showing up in the English language. For instance, what's the most common letter in the English language?
E.
E. So likely the most common letter in any message is going to be E, and then you can try to figure it. You just play Wheel of Fortune. You just do the Vanna White thing, and eventually you can figure out what the message is by mathematical analysis. Andy?
I was just saying, yeah, almost just like that.
Yeah. It's like Hangman, right? Yeah. It seemed like you wanted to add more too.
No.
Okay. All right. Yeah. Good. So it's not particularly good for any fair-sized messages. For a short enough message for one block, it could be decent. All right. Now you mentioned chaining, Greg. What is that?
So taking the output of a previous stream and putting it as the inputs in the next cipher. Sorry.
Good. And that allows you to add a whole nother round of complexity to it, right? Good. When we had this diagram up, we're chaining it basically, right? Good, because we're feeding the newly encrypted stream into that cipher again. Good. What's cipher feedback? What's cipher feedback instead of chaining? What's the difference between the two? We're using it as the key. Instead of using the blocks themselves, we're using the encrypted block as the key for the next block. Does that make sense? Less or more secure than cipher block chaining?
More secure.
More secure, because you're using it, again, as another layer of complexity, something else that couldn't be guessed. You're adding another variable to it. Yeah.
So, question with that: what's the block as well, right? So, what are you going to encrypt? Are you using it as both the key and the block?
You're using it as the key and the block.
Oh, okay.
Yeah. Output feedback and counter, and we're going to delve into those in a little more detail too. Those can be you already have your key when you go into the process, so you can store those and reuse them. Less or more secure? Less, because you already have it, and it's something that you're going to reuse, right? Good. What's a null cipher? When you have a default encryption system and everything has to be encrypted, sometimes you don't want to encrypt, and sometimes you have to tell the system, don't encrypt it. So you're running it through the encryption process with a null value, basically saying, don't encrypt this one. It includes a subset known as the concealment cipher technology. Do we use that anymore? Is it good for anything in terms of actually concealing information, protecting confidentiality? No. It's children's games kind of stuff. It's not useful at all. Substitution ciphers. We talked about this. The Caesar cipher is a substitution cipher. All we say is move 3 characters along the alphabet. Move 5 characters back along the alphabet. It's also referred to as ROT13 because there are 13 characters in Latin.
ROT 13 is different. Caesar cipher is ROT 3, technically.
Yeah.
Yeah, ROT 13 is taking half of the alphabet, so like your A becomes your N. It's just a 13-letter shift down the character base.
Okay, all right.
Yeah.
Okay. Yeah. Yes. Okay. We're also going to talk about mod, too, and that's similar to that concept. You're shifting the alphabet. You're going to offset the alphabet. Yeah. Okay. Playfair cipher uses this concept. Let me put that up there. Playfair uses an arrangement. It's an actual physical location of the alphabet based on a given word. you pick a word as your key. In this case, they're going to use the word triumph. And you take those letters from that word and you spell it out across. In this case, because we want a 5 by 5 block, we use I and J as the same letter. After you spell your word out, after you use your key, then you spell the rest of the alphabet, ignoring those letters when you come to them, just skipping over them. Then, when you're sent a message, in this case, do not accept offer, you encrypt it by going to the block where those letters are and offsetting it by the letters next to them. In this case, you have, for instance, you have D and O would be your first block. You could use the letters F and L as your ciphertext, because D and O are here, F and L would be your next block. You'd transpose it based on the corners. And you do that for every group along the way. Does that make sense? No?
And when you have 3 letters, like the not,
all you're doing is you can pad out the message. Sorry, here, this is not making it to the message. You would parse your message into 2-letter blocks, and you could pad it out by using X as a filler.
okay.
Does that make sense?
Yeah.
Okay. Good question.
But then what if you want to use X?
Then you'd use X.
See, the point there is that they're really only using the X on the double letters. Mm-hmm. So whenever you've got 2 C's next to each other, they don't actually form a block.
Yes, because there would be no block. There'd just be C and C.
Okay.
Does that make sense?
Yeah.
Okay. Cool. All right. It's not very complex. It's fairly easy to decipher that as an attacker. Transposition is another way of doing it. We're going to move the letters in the plain text around to give us a new ciphertext. For instance, rail fence is one technique. We're going to write our message in 2 rows, shifting and offsetting. Our plain text is, this is the best class. So we're writing it this way. This is the best class. This ends up being our ciphertext. Our key is the number of rows, because we can write that with however many rows we want based on the length of the message. Again, not a very strong cipher. It can be decrypted pretty easily. But we can combine these concepts to get a different layer of complexity. You can also use rectangular substitution. You agree with your recipient what that table is going to look like ahead of time. That becomes your shared secret. That's your key. In this case, we're going to write it down, go back up, and start again. I'm sorry, we're going to start from left to right, and then we're going to go to next rows. So if we change our plain text to our ciphertext, we're going to read down and then go over and go down. You could also go down and go over and go up and do it serpentine like that. It depends how you want to arrange it with the recipient. That's, again, your shared secret. So your ciphertext becomes this gibberish. We talked a little bit earlier about monoalphabetic and polyalphabetic. If you use the same alphabet for all your substitution, frequency analysis is still going to pop up. Again, the letter E is still the most common throughout. It makes it a lot more difficult if you use more than one kind of alphabet. Switching to a different language, switching to a different numbering set. It still makes it more difficult. You could still be vulnerable to frequency analysis. It's not all that much more complex compared to modern algorithms. How do you pronounce that? Viognier? Is that right? Viognier? That guy. That guy used a table of 26 alphabets. And then the key became a given word to read along the characters of these tables. You would use plain text for your columns and the key for the rows. And then you'd map these things along the way, offsetting each alphabet by a given increment.